So in this video I'd like to discuss the importance of symmetry. So aside from being beautiful and therefore appealing, symmetry is actually a very useful idea in math and physics. Okay, usually it allows us to simplify what initially seems like a very difficult problem. Okay, so let's take this as a quick example. Okay, let's say you were asked to sum the numbers, okay, from 1 up to any number that you choose. Okay, is it possible to come up with an equation that would do the job for us? Okay. Initially, this seems well relatively quite difficult. How would you try to answer this question? Okay. Well, what you could do is break it down into a smaller problem. So in the beginning, you might ask yourself, well, how would I calculate 1 plus 2 plus 3 plus 4 plus 5, say? Okay, and this is something we can obviously easily calculate. You can just add the numbers or use a calculator. So 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15. Okay, so we know the answer is ultimately 15. But if we want to use symmetry in this situation, we have to try and move this question into a more visual construct. Okay, so what if I drew dots representing each of these numbers? Okay, watch what might happen. If I draw one dot here for the 1, 2 for the 2, 3 for 3, 4 for 4, and 5 for 5. Okay? Now you might see I've just arranged them into a diagram like this, one on top of the other. So you might see that symmetry might come into play here in some sense. Okay, why? Well, how does this help us, in other words? It helps us because if you look at this, it looks like a triangle that's half, maybe, of some kind of rectangle. Okay? So what happens if I take this leap? What happens if I duplicate this triangle and put it on top of itself? Okay, if I start by writing a 1 here, okay, and a 2 here, and a 3 here, and a 4 here, and a 5 here. Okay. Now I've made the object into a rectangle. Okay, this helps us for the following reason. Okay, instead of adding like this, when you have an array that's rectangle or square, you can use multiplication instead of addition. Okay, so watch. Along this side, I have 1, 2, 3, 4, 5, 6 dots, and along this side I have 1, 2, 3, 4, 5. Okay, we have an extra dot on this side because I have to fit in the duplicated triangle. Okay, so we have a rectangle here, and when I have a rectangle, I can find out the total number of dots just by multiplying the number of dots along this side by the number of dots along this side. Okay, in which case I get 5 by 6, which is 30. But remember that we only were initially adding the triangle, okay, the first half of these numbers, right? So we have to divide this by 2. Divide by 2, and we get 15, the same as we knew it would be, okay? But the beauty of this is that we can generalize this argument. Okay, we could have had any sum here, any sum at all. It could have been up to 10 or 50 or 100, it doesn't matter. Okay, what we want is a general formula using this approach. So if this was up to 50, of course, we would have an array that kept going all the way down here until this number was 51, you see? So this provides an easier way to calculate sums, okay, through multiplication. So let's generalize it. We initially were counting in our example, we were counting up to 5. And this, the number of dots vertically, this was the same number, 5. So we're going to call this n, okay? N for the final number that we count until. Okay, and this number is 1 more than that. So this one will be n plus 1. Okay, so no matter what the number, this is the number we count to, and this is 1 more than that. Okay, it doesn't matter what the final number is we take. Okay, in which case, what did we do? Well, we multiplied n, this number, times this number, n plus 1, and we divided by 2. Okay, that is a general formula for the sum of integers, sum of natural numbers, I should say, up to any number n. Okay, in math speak, we sometimes write this as the sum from k equals 1 to n of k. Okay, but don't worry if you don't understand this notation. This is just for those of you who do. This expression is actually very famous. So anyone doing sequences in series, studying sequences in series in SAT or A levels or Leaving Cert, you'll memorize this formula. Okay, it's one of the more popular ones, but most of the time they don't explain where it comes from. And symmetry allows us to derive this this equation really very easily. Okay, good. Another symmetry problem, or rather another problem that symmetry can help us with, is this. We discussed before the symmetries of the equilateral triangle. Okay, so there are 3 lines of symmetry. It looks as though these lines meet in the middle. Okay, so what if you were asked to prove mathematically that this was true? What if you were asked to prove that these lines meet at a point? Okay, that might be quite difficult if you were to try to answer this question using algebra or some other means. Okay, but it becomes relatively easy when you consider symmetry arguments. Okay, so take this simple argument. If you take, for example, you can start with any of them, but let's just take the vertical line of symmetry. If I fold this triangle over onto itself across this vertical line of symmetry, it fits neatly onto itself. Okay, that's more or less our definition of symmetry. Okay, well that means that that point at the center there, that will be on the crease. It will be on the fold itself. Okay, but that's true no matter which line of symmetry you choose to fold over. That point must be on the crease. Okay, that's the definition of this line of symmetry. Okay, so you can see how this fact forces a convergence at this point. Okay, and if you can think about it from the opposite point of view, let's say perhaps in this example that they did not meet for whatever reason. Okay, let's say that 2 of the lines meet at a point, but the vertical axis doesn't meet at the same point, right? Well, in this case, it completely breaks the symmetry of the equilateral triangle, okay? And it would allow you to determine that the triangle has been transformed in some way, okay? Why? Let's say these 2 lines of symmetry join at this point here, and I mark it with a point, okay? That's visible front and back, right? But then, if I flip this triangle, that point will move over to the other side. So I can now see whether it's on the front, if you like, or the back. And it's broken the symmetry of the triangle. Okay, an equilateral triangle should be perfectly symmetrical across 3 lines of symmetry. So this is impossible, and therefore they must all meet at the point in the middle.